Hello everyone. Myself Dr. Amit Sharma, working as a professor in Civil Engineering Department of IPS Academy Institute of Engineering and Science. Today we will learn something about experimental stress analysis. The basic two methods of analysis are analytical method and experimental method. We will concentrate on experimental stress analysis. For that we need to go to know the importance of basically the experimental stress analysis. Actually, we live today in a complex world of many structures and machines. We work in buildings which may be many story high, 8 story, 10 story, 12 stories, and travels in cars, ships, trains, planes. We build huge bridges and concrete dams and send mammoth rockets to the space. Such is our confidence in the modern engineering that we take these many structures for granted. This attitude of mind is a tribute to the competence and reliability of modern engineering. Well, we have the methods of design of structures. Basically, three main methods which we are using are: first is initial working stress method, followed by ultimate load theory, and then finally the limit state method. It is always said that for a new civil engineer to work under experienced engineer so that he can learn the design from his experience and work. Thus, when a civil engineer is dealing with familiar design problems and following conventional practice and following the codes, the engineers draws on past experience is in assessing the strength that must be built into a structure. A competent civil engineer, for example, has little difficulty in selecting the size of steel girder that he needs to support a wall because it is something different from his regular practice or conventional practice. When he departs from conventional practice, however, and is called upon the design of unfamiliar structures or to use new material or techniques, the engineering can no longer depend upon past experience. So the mathematical analysis of the stresses in complex components may not in some cases be a practical proposition owing to the design of high cost of a computer time involved. Although right now we have a very good computer system also, so we can do that. But there are something we need to give to the computer to solve any problem. These are called input data. So if we don't have input data, then also it is difficult for a computer to solve the problem for us. For example, if we want to perform or to obtain the premium of any structure, suppose a masonry structure, let us take an example of masonry structure. For that, if we need to get the premium amount against earthquake for any masonry structure, then we have to perform the fragility analysis. Fragility analysis depend upon the time history analysis. Time history analysis, we need the input data as what we need as an input data. We need the nonlinear property of that particular material. Suppose masonry, and the masonry properties are varies from place to place. So we can't rely on the properties that are available in the system or are or in a software like STAD, SAP, Abacus, etc. So for that we need to calculate these properties, and these properties cannot be calculated until we are not performing the experimental stress analysis to obtain the stress strain curve of the particular material as masonry in our case. So if the engineer has no other way of assessing stresses except by recourse of the nearest standard shape and hence analytical solution available, he builds in greater strength than he judges to be necessary. Thus, that is by incorporating high factor of safety in the hope of ensuring that the component will not fail in practice, which means unnecessary weight, size, and cost, not only in the component itself, but also in the other members of the structures which are associated with it. So, for example, there's a shake table test which we are usually performing against the particular times to or the times to of high frequency. So, what we need to do in that case, we have to make a model, either full scale model or a prototype model, and then apply and need to apply the time history on check table. So we will see its performance, whether it is fail or not. If it fails, then again what we need to do, we have to retrofit it and again check the performance. So this is an example. So in order to overcome this situation, engineer make use of experimental techniques of stress measurements and analysis. Some of these consist of reassurance, means testing of completed structures which have been designed and built as the basis of existing analytical knowledge and past experience, which the example of check table which I am saying. Over the past few decades, this experience, stress analysis or strain measurement techniques have served as increasingly important role in aiding designer to produce not only efficient but economic design. Now, the different methods of experimental stress analysis available are brittle liquors, strain gauges, photoelasticity, and photoelastic coating. Photoelasticity, we have already learned that in photoelasticity, what we used to do, we made a model, small scale model of a particular material which allows the light rays to pass through it, and by using different light sources, maybe white light or sodium vapor lamp, we'll see the fringes, and the fringes will calculate the stress strain developed in that particular model. Now presently we are concentrating on strain gauges. Let us some examples. This is a tower. Experimental has been done. In this tower, to measure the different parameters at the University of Peradeniya, and that similar model is then developed in finite element model in a particular software, and this different color shows the different stress values developed. So we can perform experimental as well as in the software. Now these are the experimental stress analysis using advanced computer aided design. This is of steel structures, and this is concrete and composite structures, which we perform using STED also or SEP. Now this layer which we see is, this is the temperature variant in a cup when we pour a tea into it. Similarly, we have seen in movies also that during the, by using night vision camera, we can see a different color combination. A man having different color combination. This is basically the temperature variation of a particular human body. Now we will study strain gauge extensometer here. Also, how extensometer works, measurement of solid mechanical properties, strain measurement, measuring system, electrical strain gauges, and its principle involved in it. So, first of all, strain gauge extensometer. We need to understand Hooke's law. What is Hooke's law? It states that within the elastic limit, when a force is applied on a body, then the stress produced in the body is directly proportional to the corresponding strain developed in it. What do you mean by stress? Stress is nothing but force per unit area, and strain is known as the ratio of change in length to the original length. And what is it? These extensometers. It is a device that used to determine changes in linear dimensions. Electronically measures extension of sample under load. From load and extensometer data, we can get the stress versus strain curve. Also, the tensile or compressive yield and ultimate strength. And finally, we will get the modulus of elasticity, which is nothing but the ratio of stress to strain. How does it works? The basic principle for a resistance type transducer is that the resistance of wire increases with increasing strain and decreases with decreasing strain, and thus corresponding change is measured. What are its uses? It is used in measuring deflection of machines, grip deflection, and also nonlinear stress strain curve generation for masonry and other civil engineering materials. Now, this is the system. How to measure? First, we need to know the parameter to measure. For example, we are taking solid mechanical parameters. In that, we can calculate stress, displacement, velocity, rotation, acceleration, force, and torque. Then we need a sensor that will sense these parameters. It may be a strain gauge. Then a conditioning or transmission system and a recorder, which combinedly forms a data acquisition system where we can get these readings either in volt or ampere. Here we are concentrating on measuring the strain. Now, what is strain? Strain is nothing but the amount of deformation of a body due to force. More specifically, it is defined as fractional change in length. When a force is applied to a structure, the force is applied, the component of the structure changes slightly. That is, the length L is changes to delta L. The device to measure these small changes in dimension are called strain gauges. And presently, we are going to study electrical strain gauges or electrical resistance strain gauges. The ideal sensor for the measurement of strain should have a good spatial resolution to read, implying that the sensor would measure strain at a particular point where we need to measure it, be unaffected by change in ambient condition, temperature, and other variations, have a high frequency response for dynamic strain measurements. A device that closely meets these characteristics is a resistance strain gauge. This is the resistance strain gauge. These are available in the market in this form, and this is the detailed gauge grid width, overall length. Then further it will increase or decrease. So basically, a strain gauge is a device whose electrical resistance varies in proportion to the amount of strain in the device. The most widely used gauge is the bonded metallic strain gauge, which we are seeing here. The electrical resistance strain gauge is an extremely common device used to measure strain in a structure and also a sensing element in a wide variety of transducers, including those used to measure force, acceleration, and pressure. Right? That is basically strain is measured in micro strain. It may be a negative or positive depending on the force we are applying. If we are applying a tensile force, suppose let us take a sign convention, it may be a positive. If we are applying a compressive force, it may be a negative. So to understand the function of a strain gauge, consider the measurement of strain in a simple structure and a beam. A force is applied at the center and the beam is deflected. Right? If strain is a unitless quantity, okay. Now see, the total length is L, change in length is delta I, strain is change in length upon original length, and stress is modulus velocity into strain. With the type of loading, the beam will become longer at the bottom as it is experienced tensile force and shorter at the top of the surface as compression force is there. A wire is attached to the beam using two standoffs function as a simple strain gauge. Considering its original length L, when the beam is loaded, its bottom portion, as I explained earlier, comes in tension and top portion come in compression. Thus, there will be change in length from delta L as delta L from L, increase or decrease depending upon the condition in which it is having. In the above case, the strain and the lower surface will be, as I have explained it earlier, will be tensile and above it will be compressive. So the stretching of wire in upper portion and shrinking of wire in the lower portion, it will give us strain, serve as a strain indicator. If strain, basically strain is a unitless quantity and it is generally very small. For example, a particular for a steel, it is along 0.0014. Its unit is microstrain. These are the strain gauges, also termed as load cell, invented by Edward Seaman and Arthur C. Rouge in 1938. So These can be connected electrically, and the relation which you are having is this is in tension, this is in compression. Change in length will be will directly proportional to resistance. So this relation we are having, R is equal to rho into Ly, where R is the resistance directly proportional to the length, rho is the property of material, L resistivity, L length of wire, and A is effective cross sectional area of wire. This is an example showing extension or shrinkage, tensile force and compressive force. So various gauge applications are measurement of pressure, force, small displacements, torques, and load. Now, what is the principle? So let us take a metal conductor. Let us suppose there is a metal conductor is stretched or compressed. Its resistance change on account of the fact that both length and diameter of conductor changes. If a tensile force is applied, then the length increases, diameter decreases, and vice versa. And we know the relation R is equal to rho L by A, right? So it's a metal conductor having length L, diameter capital D, tensile force is applying, length changes to delta L. Now let the tensile stress is applied to the wire, which results change in length L to delta L, small areas delta and diameter is delta D. In order to find delta R, where R is differentiated with respect to F stress. So we get this relation del R by dLs is equal to rho by A del L by del S minus rho L upon A square del A by del S plus L upon A del rho by del S. Now dividing equation 2 throughout with R is equal to rho L by A, we get this final equation. Now in equation 3, per unit change in resistance is due to first per unit change in length, that is delta L by L, per unit change in area delta A by A, and per unit change in resistivity delta rho by rho. Okay. Now area we know pi by 4 d square. Differentiating with respect to S, we get this equation. Now dividing both sides by A, we will get the final equation. Now putting this value in equation 3, what we have this, we'll finally get this equation 6, 1 upon R dr by ds is equal to 1 upon L del L by del S minus 2 by D del D by del S plus 1 upon rho del rho by del S. Now we also know that Poisson's ratio mu is equal to ratio of lateral strain to longitudinal strain. Here we get minus rho d by d upon rho L by, sorry, del d by d by del L by L. So finally we will get the value of del d by d, and that value will put in equation 6. This equation will finally get this value, and here finally what we get is del R by R is equal to del L by L plus 2 into mu into del L by L plus del rho by rho. If we will make del R by R upon del L by L as GF, that is gauge factor, and we know strain as del L by L, then finally we will get this equation del R by R is equal to gauge factor into del L by L is equal to gauge factor into strain. So the final gauge factor value is 1 plus 2 into nu, that is Poisson's ratio, plus del rho by rho upon del L by L. As the strain is terms of microstrain is very small quantity, so we can neglect this, and finally gauge factor is equal to 1 plus 2 into nu, that is Poisson's ratio. Similarly, we'll get for a deflected beam the different values as of axial, the different values in terms of axial strain, transverse strain, strain gauge factor, and strain gauge equation. which we can use in different numericals. So gauge factor for different materials we are having for nickel, soft iron, etc. So we can take these values in our calculation. So let us take an example. A resistance wire strain gauge uses a soft iron wire of small diameter. The gauge factor is plus 4.2. If not given, we have to find out. Neglecting the piezoresistive effect, calculate the Poisson's ratio. So we know the gauge factor 1 plus 2 mu plus del rho by rho upon strain, as it is a very small quantity. So neglecting piezoresistive effect, we get gauge factor is equal to 1 plus 2 into mu. We know the gauge factors. Finally, the Poisson's ratio is 1.6. So the different, now we'll see the other types of strain gauges. As first is mechanical strain gauge or extensometer using optical or mechanical lever systems. Another is pneumatic strain gauges using changes in pressure. Then acoustic strain gauges use the change in frequency of a vibrating wire. Semiconductors or piezoresistive gauges are using the piezoresistive effects in silicon to produce resistance changes, and the inductance gauges using changes in inductance of, for example, differential transformer systems. Also capacitance gauges, which are using changes in capacitance against two parallel or near parallel plates. So right now we are stopping here, and then we will see different types of strain gauges also in the next lecture.